Today's video is all about reviewing for the final. So I'm going to start with chapter 1 material and then move my way on up. So the best way to study for the final would be to look at the review, and that's what I'm doing right now. So there is a link to the review. It's the final exam review for Chem 1303. It's several pages long. At the end of the packet are appendices, or an appendix, with naming covalent and ionic compounds, scientific notation, significant figures, that flow chart for converting between atoms and molecules, moles, mass. There's the solubility tables, everything you would need to help you study for the final. So I'm going to go through this packet, and then there's also a practice exam, which is 60 questions long. So it's almost as long as the actual final exam, so I recommend you take that as well. The other material that would be helpful is past exams. Okay, so any of the exams that we have taken, review those. If you got any questions incorrect, figure out why, because it's going to be the same types of questions on the final. So we're going to be going through this review, so the numbers that you see here, they're following along with this review. Okay, so the first part of the final exam review talks about temperature conversions. So it's been a while since we've done those. And for temperature conversions, you need to be able to go between Fahrenheit, Celsius, Kelvin, and back again. Okay, so you have an equation sheet. There's an equation sheet posted with all the equations you're going to need on the final exam. So you would look at the temperature conversion area to solve this problem. And I'm only going to do one example, but I'm going to do the hardest type, so that you can see how that looks. So this first one is going from -5 degrees Fahrenheit to Kelvin. Okay, so this is the hardest type of temperature conversion because we can't go directly from Fahrenheit to Kelvin. We need to go to Celsius first. If you look at your equations, so up here I'm just going to write kind of the process. So I'm going to start at degrees Fahrenheit because that's what I'm given. I'm then going to go to degrees Celsius. Once I'm at degrees Celsius, then I can get to Kelvin. Okay, so it's 2 steps. So I'm going to need 2 different equations for those 2 steps. So the first step, when I'm going from Fahrenheit to Celsius, I need the equation where Celsius is equal to, because that's what I'm solving for. So I'm going to use degrees Celsius is equal to, and that's Fahrenheit minus 32 on the top divided by 1.8. Okay, so all we need to do is plug this -5 degrees Fahrenheit into this equation. So on the top I have a -5 for my Fahrenheit, so I put that in for F, subtract 32 from it, and divide by 1.8. The trick with this equation is make sure that you put parentheses around that subtraction, or else just do that subtraction first, because otherwise order of operations is going to do the division first and then the subtraction, and you're going to get the incorrect answer. And you can bet that the incorrect answer will be one of the choices on the multiple choice. So I do that subtraction first to get -37, and then I divide that by 1.8. And I'm going to get -21 degrees Celsius. Obviously, I'm not doing significant figures here. All right, so this is the first step. I'm at degrees Celsius. Okay, but it's asking me to go to Kelvin, so I have one more step using this degrees Celsius. So to get to Kelvin, step 2, I need an equation where Kelvin is equal to, since that's what I'm trying to solve for. And to figure out Kelvin, we've been doing this even recently in those gas law equations. We take degrees Celsius and we add 273 to it. Okay? So we're going to take this -21 that we solved for in step 1 and add 273. Don't forget the negative sign. And I get 252. Okay? Now, if you didn't round up to -21 and you left it at -20.555, that's fine. These numbers, these answers in the multiple choice are going to be far enough apart, but pick the closest one. Okay, so if you get 251 or 253, okay? You're just picking the one that's closest to your answer, because it depends where and when people round, okay? So that's it for the temperature conversion. So know how to use those equations. Make sure you're doing the practice exam, looking at chapter 1 exam that I handed back to you, and checking on those. Okay, now let's look at conversions. So conversions we've been using all semester, right? We learned it in chapter 1, and I told you the reason that we were taking so long on chapter 1 was because you needed to know this stuff for the entirety of the chapter, and it is so true. So this should be second nature to you by now, but I'm going to go through an example anyway just to make sure. So we have two types. We have metric to metric, and we have English to metric. So metric to metric, those ones you can use the shorthand way, the King Henry died drinking chocolate milk. Well, how do you know if it's metric to metric? Well, this example here has 7.1 kilometers, and we're trying to figure out how many centimeters. So you can identify it as metric to metric because it has that letter in common. Meters, meters, okay? So if we're going from kilometers to centimeters, that's metric to metric, and I can apply it using KHD space DCM. And in this case, that empty space, what's going to go there is the letter that we have in common, and we just said that was M, meters. So this is meters. Do not get that confused with this end one, which is millimeters. Okay? So when we start this, we're starting at kilometers at the K, and we're going to centimeters at the C here. All right? So to get there, we're going to move the decimal point 1, 2, 3, 4, 5 times. Okay, what direction did I go? I went to the right, so I'm going to do the same thing. So starting at 7.1, I'm going to start at my decimal point and move 5 times, just like I did up here, to the right. So 1, 2, 3, 4, 5. Okay, what's going to go in all those empty spaces? Zeros. So 7.1 kilometers is equal to 710,000 centimeters. All right, let's look at English to metric and how that differs. So we're looking at number 3 on the final exam review. So English to metric, we're going to take 0.542 pounds and we're going to go to kilograms. So looking at this, I know that it's not metric to metric. I know that I can't use the King Henry died drinking chocolate milk because there's no letter in common. I'm not going from meters to meters or from grams to grams of any sort. Okay, I'm going pounds to kilograms, completely different, right? So whenever you have English to metric, you need a conversion factor. So that's the difference. You need a conversion factor. You're going to be doing those railroad tracks that we've been using so often. Okay, so for the conversion factors, you will find a list of conversion factors on your final exam equation sheet, and those are the ones that you need to use for the exam. Okay, so we have 2.205 pounds is equal to 1 kilogram. So this is our conversion factor. It's going from pounds to kilograms, and we want to go from pounds to kilograms. So that's how I know it's the correct one. So I'm going to do my railroad tracks. So one stepper, right? Just one conversion factor, so a pretty simple one. What am I going to put in this upper left-hand corner? You always put with what you are given in the initial problem. So 0.542 lb. Now I'm going to take this conversion factor and I just need to figure out where my pounds is going to go. Do I want the pounds portion on the top or on the bottom? I want the pounds portion on the bottom because the pounds need to be on opposite sides of this horizontal line so that they cancel. So effectively what I'm doing here is I'm taking 0.542 and I'm dividing it by 2.203 because remember this horizontal line is a division line. When we go across, that's multiplication. So 0.542 times 1 and then divided by 2.205. So 0.542 divided by 2.205. 0.246. How many sig figs are we looking at? It's 3, correct? So 1, 2, 3 sig figs here. So I need 3 in my answer. So 0.246. Units on it are kilograms. All right, so that's the first part, first three problems. So let's move on and look at scientific notation. And there's an appendix that reviews the rules on the final exam review. So if you forgot some of the rules or just need a refresher, refer to the Appendix 1 to review those. So for scientific notation, we're going to take and express the answers for 2 and 3 in scientific notation. And I just erased those answers. So for number 2, so we're looking at number 4, scientific notation. Okay. The answer for number 2 was 710,000, I believe. And then the answer that we just got for number 3 was 0.246, because we stopped at 2 sig figs. Right, so this was centimeters and this was kilograms. Okay. So what number 4 is asking us is to take these numbers and put them in scientific notation. Now a lot of you have a button on your calculator that does that for you. But I'm going to go through the steps anyway because it's important to know how to do this. Because you might find yourself without a calculator and needing to do this at some point. I know you might be laughing at me right now, but it's true. So, 0.246. I don't know if you can see that. There we go. All right, so starting with this first one. So what scientific notation is, we're raising to a power of 10. Okay, so the key points of scientific notation, you always want one number, one non-zero number, I should say, to the left of the decimal. So looking at this number, 710,000, where am I going to want my decimal point? Between what two numbers? The 7 and the 1. Okay, I need it between the 7 and the 1 because that gives me just one non-zero number to the left. Okay, so now I have to write my times 10 to the exponent, what goes here. That's how many times I had to move the decimal point to get it between the 7 and the 1, right? And if there is no decimal point present, because initially there wasn't, right? I put that there. So there's no decimal point present initially, so if there isn't a decimal point right away, you look and start at the end of the number. So my decimal point's going to start here, and I'm going to move it until I get it between the 7 and the 1. So how many times do I have to move it to get it between the 7 and the 1? 5 times. Okay, well, I've moved it 5 times, so it's times 10 to the 5th. But double check, does this need to be a -5 or a +5? And remember, the rules were if the number is greater than 1, we have a positive exponent. If the number is less than 1, we have a negative exponent. So 710,000, definitely greater than 1. Okay, so we're going to keep that exponent as a positive. Now before I'm done, I want to check sig figs. Okay, so initially this number, 710,000, had how many significant figures? Remember, there was no decimal point when we started. So if there is no decimal point, do these 4 zeros count? They don't. So the 7 counts, the 1 counts, these zeros don't count because there wasn't a decimal point at the end of the number. We put one there so we could move the decimal and count places. So there's only 2 significant figures, so we keep it at just 2 in the answer. So this is the correct scientific notation of 710,000. Okay, let's move on and look at the next one. So taking 0.246 and putting that in scientific. So the same rules are going to apply. We still want just one non-zero number to the left of the decimal point. So we're going to put our decimal point between which 2 numbers? Put it here between the 2 and the 4. Okay, so I'm going to get 2.46 times 10 to the exponent. That's going to be how many times I had to move the decimal. Well, the decimal started in pink here, and I want it to be where this purple decimal is. To get it there, I'm just moving it once. Okay, so 1 is going to be the exponent. Now, do I want that to be a positive 1 or a negative 1? Well, I moved to the right this time. Not only that, but my original number was 0.2. And that is less than 1, right? 0.2 is less than 1. So it should be a negative exponent. So 2.46 times 10 to the negative 1. Last but not least, check for significant figures. Our original number had 1, 2, 3. Our scientific notation has 3 as well. So this would be the correct answer with the correct sig figs in scientific notation. Now, Appendix 1 also covers significant figures. And I know some people either love them or you hate them. So we're just going to do a few of the problems. So looking at number 5 in the final review, exam review, the multiplication and division versus addition and subtraction. Because remember, there's different rules. Okay, so for multiplication and division, are we looking at numbers as a whole, or are we looking after the decimal point? So for multiplication and division, we're looking at numbers as a whole. So in this problem, 3.70 times 1.429, since we're multiplying, we're looking at total sig figs in each of these numbers, and we're picking the smallest one. So let's count. I can figure out how many sig figs I need in my answer without even calculating it for multiplication and division. So 3.70, the 3 counts because it's a non-zero number. The 7 counts because it's a non-zero number. Does that 0 count? Well, if you look at the rules in Appendix 1, since there's a decimal point and we already started counting, yes, that 0 counts. So we have a total of 3 significant figures in that number. Okay, looking at the next number, 1.429. They are all non-zero numbers, so they all count. So we have 4 significant figures. Remembering we want to pick the smallest, so our answer is going to have 3 or 4. Well, 3 is less than 4. So our final answer should have 3 sig figs. So calculate it out, we get 3.70 times 1.429, and I get 5.2873. So let me just show you what number I'm getting here so you can see how I'm rounding it. So this is incorrect because it doesn't have the correct number of sig figs. We just said it should have 3 based off of the numbers we multiplied. So 5 counts, 2 counts, 8 counts. But 5.28 would be incorrect. Why? Because you always need to look to the number next to that final digit. So since 8 is the final significant figure, you're looking at the number next to it. If it's 5 or higher, you're going to increase or round up. If it's 4 or lower, you're going to leave that number the same. In this case, it's a 7, so that's higher than 5. It's 5 or higher. So this 8 is going to become a 9. So 5.29 would be the correct answer for that one. So that was A. Let's look at part B. So part B is addition and subtraction. So for addition and subtraction, this is usually the tricky one for most people because you're not just counting total sig figs. You're worried about just what comes after the decimal point. So decimal point only matters. So when I do these, I like to line them up. It helps me see it a little bit better. This one's subtraction, so minus and then 0.35. Okay, so I'm just going to calculate it out and then I'll worry about sig figs after that. So with addition and subtraction, sometimes you just want to calculate it first. I'm just bringing all the numbers down, okay? So when we're looking at significant figures, we're looking at just after the decimal. Okay, so how many places after the decimal in this first number? 1, 2, 3. So I'm going to put DP for decimal places. There's 4 sig figs, but there's 3 decimal places. Okay, the second one, there are 2 decimal places. So it's just like with multiplication and division, you pick the smallest of the two. So which one's smaller, 3 or 2? 2 is smallest, and so that means our answer should have 2 decimal places. So I'm going to start at the decimal and I'm going to go out 2. Look to the number next to it, that's going to stay a 5. So my answer is going to be, to the correct sig figs, 5.25. Okay, because I needed 2 decimal places. If I would have counted total sig figs, it would have just been 2 based off of this number. Okay, so you need to make sure you're looking at decimal places and not total significant figures for addition and subtraction. All right. So the next couple bullet points on your review talk about chemical properties and change. Okay, so review the definitions of those, look over some examples. With chemical properties and change, this is when atoms were arranged in new combinations. So the only chemical property we really ever talked about was flammability. For chemical change is any reaction we've ever seen, because the atoms, bonds are being broken, new bonds are being formed. Okay? For physical properties and change, well, there's tons of physical properties. So these are things that can be observed or measured without changing the composition. So you can measure the melting point or boiling point of a substance without changing the composition. So you can have an ice cube melt into water, but it's still water, it's still H2O, whether it's in an ice form, solid form, or liquid form. Okay, so melting point, boiling point are some physical properties. Volume, taking the volume of something, density, so there's a lot of those, so review those. And then physical changes, how to identify those is that they're usually reversible. So phase change is an example, so the ice cube melting, you can also freeze the water back into solid form. And then look at your definitions of element and compound. So element were the pure substances that couldn't be broken down any further. Okay, so even if you have H2, N2, even if you have S8, these are all elements because even though there's more than one atom, it's of the same element. Okay, so the difference between element and compound is compounds are 2 different elements combined. So H2O would be a compound because it has hydrogen and oxygen, 2 different elements combined. All right, and then heterogeneous and homogeneous, the definitions are there for you to review as well. When it comes to the structure of an atom, so know the parts, right? We've looked at the structure of an atom in several different ways. So we have a nucleus, and then we have rings or levels around an atom. So what 2 subatomic particles are in the nucleus in the center? Well, we have protons, represented by a P+, and we have neutrons. So both of those are in the center of the atom. Okay? Where are the electrons at? All around. I'm going to do the electrons in pink. So they can be in several different levels, right? So here's my electrons. Also know the charges. Proton, positive charge. Neutron, neutral, 0 charge. Electron, negative charge. Okay? Also know the relative masses. So protons, we said their mass is 1. When we do mass number, we count each proton as 1. Neutrons, also 1. That's why the nucleus is the dense, the heavy part of the atom, because that's where all the mass is. The protons and the neutrons, they each count as 1. The electrons, their mass is so small that we don't count it. It's negligible. All right? So these negatively charged electrons are circulating the nucleus because the nucleus overall is positively charged, because we have positively charged protons and 0 charged neutrons, so it's an overall positive. So since opposites attract, those negatives, electrons, are attracted to that positive core, causing them to orbit. Okay. With electrons, know the difference between core electrons and valence electrons. So valence electrons would be all the ones in this outer shell here. just in that outermost ring. So these are the valence. Remember, those are the ones that we use in bonding. We don't use the core electrons. So the core electrons are all of the other electrons. So the ones on this ring here, and then the ones on the rings closest to the nucleus are also core. So both of these are core. Valence are the outermost shell only. All right, let's move on to nucleus, or not nucleus, sorry, isotope. So I'm way on number 15 now, if you're following along on that review sheet posted. Okay, so we did talk about isotopes again in chapter 9, so this should be somewhat fresh in your memory. But with isotopes, know the definition, which I have written there for you. Atoms of the same element with different mass numbers, and they differ in mass number because they have a different number of neutrons. Okay. Isotopes are often represented by nuclide symbols, and that's what this guy here is. So you need to be able to use a nuclide symbol to calculate protons, neutrons, and electrons. So if I give you this, that's it. This is a nuclide symbol, right? This X is telling you it's chlorine. That's the element I'm talking about. This number 37 in the upper right, that is the mass number. Okay. Notice the atomic number wasn't given to you, but that's okay, because if you know what the element is, you can find it, the atomic number, the number of protons, with your periodic table. Okay. So the question that I'm asking here is how many protons, how many neutrons, and how many electrons? Given that symbol, you should be able to figure out all three subatomic particles given that. Well, number of protons, that is equal to the atomic number. That's the number down here that wasn't given to us. Well, that's okay, because I said you could look at the periodic table. Find chlorine on the periodic table, and the atomic number is 17. That's the number of protons. I can even write that in here. Okay, well, how do I figure out neutrons? Well, you need to know the definition of mass number. So the mass number, which two subatomic particles contribute to mass? We just talked about it when we looked at the atom. Does the electron contribute mass? No, it was negligible. So it's the protons and neutrons, those two subatomic particles present in the nucleus. Okay, so to figure out the mass number, we need to add the protons with the neutrons. Okay, so if I rearrange this equation to solve for neutrons, I get neutrons equal mass number minus the number of protons. That's why nuclide symbols are so nice, because remember when we did this way back, I think it was chapter 2, when it was written as a nuclide symbol, we could simply draw a line under here and a subtraction sign to figure out the number of neutrons. Because this is mass number, minus protons, Okay, so subtracting those two, 37 minus 17, I get 20. So there are 20 neutrons. Now electrons, how do we figure that out? Well, if there was a charge, that charge would be present right here in this upper right-hand corner. Okay, there is nothing there. So if there's nothing there, that means that this particular isotope is neutral. And if we have a neutral isotope, that means that the protons equal the electrons. So if I know my protons, I know my electrons. So 17 protons, 17 electrons. All right, well, this was just one way to represent an isotope with a nuclide symbol. There is another way, and that is where we take and write out the element name and then dash mass number. So the example given here is bromine dash 81. So let's figure out the protons, neutrons, and electrons given that symbol or that representation of an isotope. So let's do protons, neutrons, electrons. This 81, that's the mass number. That's all it's giving me. But wait, it does give me the name of the element. And if I know what element I'm talking about, I can figure out the atomic number looking at the periodic table. My atomic number is my number of protons. So finding bromine, it's a halogen in group 17. I see it has 35 for its atomic number, so that means it has 35 protons. Well, it's neutral. You can't write or represent an isotope in this fashion, element name dash mass number, unless it's neutral. So I can figure out my electrons right away as well. 35 protons, that means I have to have 35 electrons so that they cancel out and make this neutral. Now let's look at the neutrons. So neutrons, we're going to use the mass number, again, that equation that we have up here. So I have mass number equals my protons plus my neutrons. So my mass number, that's 81. That's what comes after the dash, right? So I'm going to put an 81 in here. Protons I figured out from looking at the periodic table. So to figure out neutrons, I'm doing what I did up here. I'm taking my mass number and I'm subtracting out my protons. So I'm subtracting 81 minus 35. Okay, so 81 minus 35. I get 46. All right, so moving on to 18, the periodic table. Just know how it's arranged. I mean, you're having an online final, so you're going to have your periodic table color-coded how you want it. So you should know where the metals are, where the semi-metals are, where the non-metals are, all of that information. Okay. Also know how to do electron configuration. Long version and noble gas shorthand. So review those questions, review how to do that. I'll go over two quickly here just to kind of give you a refresher of what electron configuration is. It's been a while since we've done it. So looking at the problems under number 19 here. So 19A gives you the shorthand version of electron configuration. And it's asking, given this electron configuration, which element is being represented? And when you're given an electron configuration and asking to find the element, the only piece of information you really need is that last piece there. Okay? So it's saying, start at argon. So I'm starting at argon. From argon, it says go into period 4. So I go into period 4. I hit the S block first. Remember these two, the alkaline earth metals, that's the S block. It's saying 4s2, so go 2 into the S block. So I'm at calcium. Then I hit the D's next, these transition metals. But why does it say 3D? I'm in period 4. Okay, remember, the D's are always one less than the period they're in. Okay, so I hit 4s2s, and then when I hit the D's, it goes down one level. Since I'm in period 4, it's the 3 D's. So I'm in the D's, I have to go 5 in. So 1, 2, 3, 4, 5. I hit manganese. All right, let's look at the next one, part B. Electron configuration of aluminum. So I'm going to write it the longhand and the shorthand way. So you need to find where aluminum is on your periodic table, and it is in the 3p block. Okay, so I'm going to have to go all the way there. But if I'm doing it longhand, I want to start in period 1. I always hit the S's first, so I'm going to hit 1s. Period 1 just has an S block, and remember, S block has a maximum of 2. So if I say 1s2, I'm at helium. That's it for period 1. I then go down to period 2. I hit the S's first, and remember, S has a max of 2. So if I go to 2s2, I'm at beryllium, Be. Okay, well, I'm still in period 2. If I keep going across, I'm hitting the P's. Is aluminum in the 2 P's? It is not, okay? So that means I need to go all the way through that P block. How many is in that P block? 6. That's the max that can fit in the P block. So 2P6. I'm now at neon. Then I go into period 3. I hit the S's first. I want to go all the way through the S's because aluminum's not in the 3S. So now 3S2, 2 being the max in the S. I'm at magnesium. I'm still in period 3. I hit the P block. Well, aluminum is in the 3 P's. Which one? The first one. So it's 3P1 because it's saying go to period 3, go to the P block, and it's the first one in. So this is describing aluminum. If you wanted to do it shorthand, what you need to do is look at the noble gas in the row above the element that you're searching for. So if I'm looking for aluminum, the noble gas in the row above, so aluminum's in period 3, so I'm looking at the noble gas in period 2. The noble gas in period 2 is neon. So I can start at neon, which is this whole section here. 2P6, that describes neon, period 2, P block, 6th one in. That's neon. And then, so if I start at neon, I just need to write the 3S2 and the 3P1. So this is the noble gas shorthand way to describe aluminum. And remember, if you do it the long way, and you count these superscripts, they should equal the atomic number of aluminum, as long as it's neutral. Adding those together, I get 13. Atomic number of aluminum is 13. So that's kind of a way to double check your work there. All right, so next we're gonna go into naming compounds. So appendix 2 is a good review there. So now we're on number 20. So we just covered electron configurations, and we're going to look at covalent, ionic, so definitions of those, as well as naming them, and also, given the names, turning that into a chemical formula, which we've practiced a lot since then. So appendix 2 goes over the rules on naming. I will do a quick refresher and name a few, but you can always refer to those if you need more in-depth explanations of the rules. So this would be appendix 2 in the final exam review. So we're going to start by naming a covalent compound. So how do you know if it's covalent? Well, 2 nonmetals. Okay. You need to know whether it's covalent or ionic before you name it, because remember, covalent and ionic have different naming systems, different ways to name them. So for covalent, we're using prefixes. We also have an IDE ending on the second element present. Okay, so given this chemical equation, P2O5, well, finding phosphorus and finding oxygen, they are both nonmetals. Based off where they're located on my periodic table, I can figure out that they're both nonmetals because they're to the right of that zigzag line. Okay, so since they're 2 nonmetals, this is covalent, so I'm going to be using prefixes, and I'm also going to be using an IDE ending on that second element. So phosphorus is my first element. The prefix is telling us how many phosphorus atoms are there. So it's saying there are 2. So my prefix for 2 is di. Now, since phosphorus is the first element, I'm going to write it just how it's written on the periodic table. No alternate endings for that one. So I have diphosphorus, 2 phosphorus atoms. Now, the next element is oxygen. Well, since it's the second, I need an IDE ending on that oxygen. So it's going to be oxide. But I also need a prefix indicating how many oxygen atoms there are. And there's a 5 as a subscript telling me there are 5 oxygen atoms. So the prefix for 5 is penta. So pent, ox, and then don't forget that IDE ending. So the correct name for that chemical formula, P2O5, is diphosphorus pentoxide. Now let's look at ionic. This one has a lot more rules because there's a lot more variations. So with ionic, these are when a metal is involved. Metal and a non-metal, metal and a polyatomic, okay? There's transition metals, main group metals, lots of different rules. So since metals take up most of the periodic table, there's going to be a lot more rules for naming ionics, since ionic compounds have a metal in them. So let's look at the examples given and name those. So with ionic, there are no prefixes. Okay, so no di, tri, tetra, anything like that. And there's also the IDE ending though, so that part stays the same. We still need the IDE ending on the second element, just like with covalent. But also you need to pay attention to other factors. Is there a polyatomic involved? If there is, make sure to look at your polyatomic table, label it correctly. Is there a transition metal in there? If there is, that transition metal needs to have Roman numerals indicating its charge. Okay, if it's not a transition metal, so if it's a main group metal, alkali or alkali earth, do not put a Roman numeral because we know the charges of those. It's the transition metals in the D block that have multiple or variable charges. So my first example is NiCl2. Okay, so I'm going to look at my periodic table and find these two elements. So Ni is nickel, no prefixes. However, when I find nickel, I notice it's in the D block. It's a transition metal. Transition metals need a Roman numeral indicating their charge. Okay, so I need to figure out what the charge is on that nickel. So to figure out the charge on that nickel, I use my partner here. I don't know what nickel is, question mark, but I do know what chlorine is. What's chlorine? It's a halogen, so it's a -1. Okay, so how many chlorines do I have? I have 2. So I have 2 -1 charges for a total of -2 on the anion side. I only have 1 nickel atom. I don't know its charge. But since I know the compound's neutral, I know that on the cation side, I have to have a +2. So that the -2 and the +2 cancel each other out. So that means that this whole +2, since there's only 1 nickel atom, needs to go on the nickel. Okay, so I have nickel 2. So that's the Roman numeral indicating the charge, 2. And then chlorine is the second element, so I need to add an IDE ending to it. So nickel 2, chlorine becomes chloride. All right, let's look at the next one. So the next one we have Cu2O. Looking at my periodic table, Cu is copper, also a transition metal. So I'm doing the transition metal ones mainly because these are the ones that people find most difficult. So for this one, I need to do the same thing. I don't know what copper is. Okay, so let's just first write how many coppers I have. So I have 2 coppers, right? But I don't know their charges. I have 1 oxygen. Do I know the charge of oxygen? Well, I can figure it out if I have a periodic table. So if I look at my periodic table, it's 2 away from being a noble gas, so it's going to be a -2 charge. So I have a total of -2 on the anion side, which means I need a +2 on the cation side to cancel out that -2. So it's a little different this time because this time I have 2 metals, 2 coppers. So that means each copper has to have what charge to total a +2? Well, each copper is going to have a +1 charge. So if I get a +1 plus a +1, then I'll get a +2. So my copper is a +1 copper. So I'm going to put a Roman numeral of 1 because that is the charge on my copper. Oxygen, second element, is going to have an IDE ending and become oxide. Right, let's do the next one. So similar, I have copper again, so I'm going to need to figure out what the charge is, the Roman numeral. And this time, I'm doing the same thing, but I only have one copper this time. So let's see how that looks. So I have one copper, don't know its charge. I have one oxygen, we just said it was a -2. So what does copper have to be to cancel out that -2? Has to be a +2. So this time, since I only have one copper, that entire +2 charge is going on that one copper. So this is copper 2 in this chemical equation. So whereas the previous one was copper 1 oxide, this is copper 2 oxide. So they are different. That's why their chemical formulas are different. Their chemical formulas are different, their names need to be different. Now I'll add another one just for fun. You know me, I'm all about fun. Alright, so MgSO4. I wanted to do this one because all I've done so far is transition metals, and I haven't done any polyatomics, so I wanted to show that. So how do I know this is a polyatomic? Okay, well first off I have my metal here. This is magnesium. If I look that up in the periodic table, it is a main group metal. It is an alkaline earth metal. Since it's a main group metal, I do not need Roman numerals. So do not do Roman numerals on main group. I know I have a polyatomic because I have 3 elements present in this chemical formula. If I have more than 2 elements present, that means there has to be a polyatomic in there. So my polyatomic portion is this SO4. So I'm going to go to my polyatomic table, look up SO4, and that is sulfate. Notice I write it just how it's written in the polyatomic table. I don't change it to IDE like I did with elements from the periodic table. So polyatomic table do not change, they stay the same. Alright, so this is formulas going to names. So to finish off chapter 3, let's look at names being given and converting those now into chemical formulas. So we have manganese 4 oxide. So for these ones, when it's an ionic compound, you want to make sure to write the symbols and the charges and then crisscross them. If it's covalent, the prefixes will tell you. So this first one I know is ionic for several reasons. It's a metal and a nonmetal. The fact that it has a Roman numeral tells me it's a transition metal, so it has to be ionic. Also, no prefixes. Okay, so several different ways to figure out this is ionic. So manganese, looking it up on the periodic table, is Mn. That's its symbol. Remember, with ionic, we want to write symbols with charges. It's a transition metal. That's why the Roman numeral is here. This Roman numeral of 4 is telling me that the charge on that manganese is a +4. The second half of the name gives me oxide, and that's just the IDE form of oxygen. Okay. Oxygen has a -2 charge. Now, looking at this, our goal is to make this compound neutral. Given the charges how they are right now, is it neutral? It is not. Do I need more manganese or more oxygens? I need more oxygens because I have +4 and a -2. Okay, so I have more pluses than I want. So I'm going to add another oxygen. What that does is it gives me a -4 now on the anion side and a +4 on the cation side. So it's neutral now. So that means I need 1 manganese and 2 oxygens. If you chose to do the crisscross method, where you take the charges and make them the subscripts, what you would have got is Mn2, because that 2 would be a subscript on manganese, then O, and that 4 would have become the subscript. So if you did the crisscross way, just make sure you're looking at the subscripts, and if you can reduce them down, do so. So we have a 2 and a 4, their common denominator would be 2. So this can be further reduced down into MnO2, which is the correct chemical formula that we got over here. So crisscross method, reduce down if necessary. All right, let's look at the next one. We have silver 1 nitride. So figure out if it's ionic or covalent. If it's ionic, you need to write the symbols with the charges. If it's covalent, the prefixes will tell you. It's another Roman numeral 1. It's also a metal and a non-metal, so it is ionic. So writing the element symbol, I get Ag. The Roman numeral tells me the charge should be +1. Now this nitride, notice it's got IDE ending, so be very careful with this, because we could have nitride, nitrate, and nitrite. Notice these only differ by that ending. Nitride is nitrogen, nitrate is NO3 with a -1 charge, nitrite is NO2. Okay, so pay attention to the endings, be very careful with that. Since this is an IDE ending, we're talking about nitrogen, the element from the periodic table. To figure out that guy's charge, you look at where it is on the table. It is in group 15. It is 3 away from being a noble gas, so it has a -3 charge. Now, you can do the crisscross method or figure out what you need more of. So in this case, we need 2 more silver, so we have a +1, +2, +3 total here to cancel out that -3. Okay, so that means we need 1, 2, 3 silvers and 1 nitrogen. Crisscross method would also work. 1 becomes a subscript on nitrogen, correct. 3 becomes a subscript on silver, correct. So that would be our chemical formula. Last but not least, let's look at tricarbon octahydride. So, ionic or covalent? There are prefixes, so that should give it away there. If that doesn't give it away, you can notice that both elements present are nonmetals. So it is covalent. So, look at the base words, figure out what elements you're dealing with. So we have carbon, which is C. The prefix tells you what your subscript's going to be. Tri means 3, so that means C3. We have 3 carbons. Hydride is just the IDE form of hydrogen, so H. The prefix is going to tell us the subscript, how many. So octa, that's 8. So C3H8 would be the correct chemical formula given that name. Alright, so that's going to cover the review for this video, covering chapters 1 through 3. I wanted to go over those a little more thoroughly since it's been a while since we've had them. The next video will be covering chapters 4 through 9. Okay, so it won't be as in-depth since we've seen, especially chapters 5 on up very recently. Let me know if you have any questions.